Hello, everyone. My name is Juliana Leung. I'm a professor with the Department of Civil and Environmental Engineering here at the University of Alberta. And what I would like to talk to you today is energy transition and the subsurface space. So a little bit about myself. As I said, I'm a professor here. So in addition to teaching students, I also have a research group, and you can see in the picture of my students. The focus of a research group is to look at creating computer programs to look at how fluids, meaning liquid and gas, and how they flow underground. So there are a lot of applications from geoenergy, oil and gas operations, geothermal, storing carbon dioxide or sequestration underground, as well as hydrogen storage. Now, so what is the subsurface? Subsurface basically underground, but what we're talking about is deep underground, like several kilometers deep underground. And we use that space for a variety of things, from oil and gas extraction to, as I said, geothermal storage. And even if you think about nuclear energy, what are you going to do with these waste, these materials at the end? You may want to store it in a place where it doesn't come back and contaminate other parts of our environment. And sometimes people would consider putting them underground. So the subsurface space is actually very useful in the context of energy and climate change. So let's first talk a little bit about energy transition. And that's a term that you may hear a lot in the news and in the media nowadays. What we're talking about is how the supply of the energy for this world may change or transition from the current state to what it would be like maybe 30, 40 years down the road. So as you can see in this chart, in 2020, majority of the energy comes from fossil fuels, so coal, oil, natural gas, and there are only a small amount that comes from renewable sources. These international agencies and various organizations around the world will do these forecasts every year and try to see what it may be like in the future. Now, the different bars that I have here, so the STEPS, APS, or NZE, they basically are an acronym for different scenarios. So for example, the STEPS one would be one where it's based on existing and announced policies. So there's a clear pathway in some way to get to that point, where the other two are more based on what they would predict if there is people have announced certain pledges, but there are no clear policies, for instance, to implement those pledges. So they are the more optimistic scenarios. But one of the things that we can see is that as we talk about transition, meaning that it is a gradual change. So it's hard to change from one point to another point overnight. But what we can do is that you can see the amount of the fossil fuel usage is actually reducing, and the renewables are making up more and more of the total percentages. But even looking at this, even at the net zero scenario, that there is still about maybe 20-something% of our energy supply has to come from fossil fuels. So the question comes is that why can't we just transition quickly? Or first of all, how can we not just go to these net zero scenario tomorrow? Or why can we not go to a scenario where it is 100% renewable? Well, there are different factors to consider. One is that the global energy demand continues to increase. So for example, if you look at forecasts by different agencies, they all point to the fact that the total amount of energy demand increase with time as we're moving forward. So the population is growing. And also there are a lot of developing countries around the world. They still are trying to increase their energy consumption to improve oftentimes the quality of living. So you can see majority on the map here, like for example, places in Africa, in parts of Asia, and even Central South America are the major customers, as you can say, for energy, and it is expected that their energy demand will continue to increase in those countries. And even China themselves, when they produce outlook of what it will be like, they will still see a increase in energy demand. It's just that by hopefully in maybe 20, 30 years that you can see that there will be less dependent on non-renewable sources, but the renewables would increase. So in addition to an increase in global energy demand, the other issues that we deal with is that energy systems are complex, meaning that energy, when we think about energy, it's not just about the energy supply. We also need to think about the other parts of the system, meaning how we consume energy, how energy is transported from one place to another. So for example, if you are right now, if you want to use oil-fueled cars, you would drive your car to a gas station, you plug it in, you fill it up, and you go. If we want to all transition to driving electric vehicles or EVs, we now have to have a different system of maybe charging our vehicles at home. We have to have more charging stations. And then now these batteries probably need to be improved so that we don't need to stop a car all the time to try to charge it. And some of you may know, if you're driving a EV to go from Calgary to Edmonton, you likely will have to stop somewhere in between, and maybe you have to park your vehicle for 45 minutes, for instance, to charge your vehicle. And if that's the case, if everyone is doing that, then our grid system may not be able to support that. And current grid system actually would not support everyone to driving EVs immediately. So this all needs to be updated. So as you continue to exercise in this event, I hope that you will also think about how the different infrastructure is needed in order to support a different makeup of the energy supply. And the other part is also technology development takes time. So if you're thinking, then why don't we just update all our batteries or have some fancy batteries like tomorrow? Well, we all remember that during the pandemic, there was, at the beginning, there was a lot of urgency of developing a vaccine. But even that, it took some time. And I think the reality is that technology needs to develop technology, we need to test things, we need to try it, and then implement it at large scale. And that's certainly takes time. And the challenges with renewables is that they are intermittent, meaning that, for example, you don't have the wind blowing at all time, you don't have the sun shining at all times. So we must find ways to store the energy. So our batteries will be one, right? But also people talk about hydrogen storage. It's basically converting the energy into putting it into an energy carrier like hydrogen, and then you store it underground and then extract it whenever you need. But in the end, the challenge is still to store them. The other challenges is also what we talk about is the energy density. So for example, coal, oil, and gas, the energy are stored in the chemical bonds of the molecule. So when we take the gas molecule or oil molecule, you put it through combustion, you release the energy, and then it is really dense, meaning that a lot of energy is packed into the chemical bonds of the molecule. However, in other types of energy, they are lower in terms of energy density. So you need more wind blowing in order to create the same amount of energy. And so all of that basically makes the need of the batteries or energy storage even more important. Finally, I think this part may be even more difficult to explain, is that all these things are very complex, and it involves a lot of trade-offs. So for example, if you think about batteries, right? Batteries often are made of some of these metals or minerals, which we call rare earth minerals, and they need to be mined. So right now, majority would come from, for instance, in China, which is not produced locally in Canada. And mining also has a lot of environmental footprint. And if you think about it, you take these metals, you make the batteries, and one day you're done with the batteries. What do we do with that, right? So the more we want to use electrify essentially our system, we need to find a way to manage these materials and recycling, and to also consider the environmental footprints of all these processes that are involved. So I think eventually the path forward is to continue to reduce the environmental footprints or impacts of whatever we're doing, but we also need to make sure that we have sufficient energy to supply the increasing global demand. And if we are using non-renewable sources, we need to figure out ways to reduce the greenhouse gas emissions. And we also need to continue to develop renewable energy sources. Now, with all of that, how is that related to the subsurface? As I was saying at the beginning, there are a lot of things that these things do involve the space in the subsurface. So for example, geothermal energy. Geothermal energy means that we often can inject cold water into the ground, and because the underground is actually hotter, for example, in the winter time, the ground will be hotter than our atmospheric conditions, and in those so in that case, you can inject cold water, and then you can pump the hot water out, and then the hot water now can be used for heating buildings, or you can also use it to generate electricity. All these things are large scale. Actually, this process can be reversed in the summer for cooling. So for example, if your surrounding area is very hot, but the underground actually is at some sort of a constant temperature, then you can put your hot air underground and cool it down and pump the cooler water out. So you can also use it for cooling purposes. So this is one way to extract energy. As I said, it can be small scale for cooling, heating for a building, or it can be much larger scale. So for instance, people are looking into opportunities for taking maybe like a depleted natural gas field and see if you can inject cold water in and then pump hot water out, because the infrastructure is already there. You already have all the wells and the facilities there, so that could be a much large scale operation. The other way that we can use the subsurface space, obviously, is also for oil and gas extraction. Now, in Alberta, we are dealing with a different kind of oil, which is often, you may hear the term bitumen or heavy oil. So basically, they are different than conventional oil, meaning that they are basically more dense, the higher density, and also thicker. It has bigger molecules, so it's hard to flow on its own. So if you think about a toothpaste being very thick, think of the bitumen being at least like 10 times thicker than that. So you just drill a well, the fluid just basically won't flow to into your well bore. So typically, in a lot of these resources in Alberta, what we do, or what the operators will have to do, is to inject steam into the well, and then you produce them. So now, but as you can imagine, steam, how do you get steam, right? You probably have to burn natural gas, so that now you use up a lot of water. You also have a high energy or carbon footprint. So an alternative would be to think of injecting something else, like other types of chemicals or even carbon dioxide, in a way to replace some of the steam. So think of this process as like if you're trying to do dishes, right? Like if you're just doing dishes, very greasy dishes, what you would do is you use hot water, or maybe you have a steam cleaner to do it. Instead of doing that, you're trying to replace some of the steam with some soap, right? So chemicals, you can think of it as kind of like a soap to combine with it so that you can rinse out the oil from underground. So that would be some of these technologies that operators are looking at to reduce the greenhouse gas emissions and water usage during these oil and gas extraction process. Another thing we can do is also to try to monitor the greenhouse gas emissions, particularly methane emissions, from everywhere. And it could be also for oil and gas productions, right? Like, so we now have satellite data that actually measures how much methane is in the air. And so one of the areas that I worked on is to look at the satellite data together with machine learning or AI to try to see if we can see where there is a high level of emissions and can we link it to certain types of oil and gas activities and see how they're doing. So large-scale monitoring of greenhouse gas emissions is also very important. As I mentioned, the other application of related to geoenergy or energy climate change underground is also storing CO2. Now, so you may hear about carbon storage or CO2 sequestration. So basically what it is that we go to the underground space, we find an area where there is very salty water. So they're so salty, they basically have a lot of these chemicals in them that you wouldn't use it for drinking purposes, for instance. And so what we try to do is to find a suitable site, and then you can inject CO2 underground. And hopefully the carbon dioxide that we inject would stay in there for a long time. So it is for capture purposes. Now, why would it stay underground? Sometimes it just, first of all, it can get dissolved into the water very much like you're making carbonated drink. Other mechanism could be that the carbon dioxide reacts with the rocks and then it basically precipitates. It's like scale, right? That you see, and then they basically deposit and stay underground. So all of these are one way to capture that. Another area is also storing hydrogen underground. So sometimes you may hear about hydrogen, and what it is that if you have hydrogen is an energy carrier. So if you store it underground, whenever you need it, you can put it back through in a reaction, and you can get electricity and water and heat. Now, the reason I say hydrogen is a energy carrier is that it depends on where that hydrogen comes from. So, for example, we don't go and mine hydrogen traditionally, right? I think recently there've been news where some in other parts of the world that they have discovered like a large hydrogen reservoir underground. So other than those cases, usually hydrogen are derived from something else. So for example, gray hydrogen would be hydrogen that you derive from natural gas or fossil fuels. So it is the energy stored in the hydrogen, for instance. And so when you need it, you put it through that reaction and you get the electricity. But you may hear about different colors of hydrogen, meaning that the color refers to the way that it is being generated. So for instance, like green hydrogen would be ones that comes from renewable sources. So there are just different colors. And we can, when we store hydrogen underground, we need to find a place where it is safe, right? Because otherwise hydrogen would become like a hydrogen bomb, right? So that can be quite dangerous. So you wanted to find an area where it is secure, but then you can also extract it easily and so that it can be used regularly when someone needs to. Another thing about the subsurface space is that in the underground, there are also a lot of other types of resource that may not be used as a fuel, but it's related to the energy business. So for example, lithium. Lithium is used a lot of time for making batteries, but lithium also you can find them in those salty water that I was referring to. So these brines or saline water underground, some of them contains lithium. So if we can produce those water out, we can take the lithium out of it, then the lithium can be used for batteries purposes. Other resource could be helium, right? So although helium is not used for as a fuel, but it has a lot of usages, and some of them will be related to the energy business. So as many of you know, helium can be used for balloons, right? So it's for lifting. It also used a lot in for medical purposes. And to produce helium, you can find basically underground gas deposits. So very much like finding natural gas, you find places with natural gas, but with a significant higher amount of helium. So you produce those, then the helium can be extracted and be used for these different purposes. Finally, there's groundwater everywhere in the subsurface. So with all these processes going on and injecting, producing things, we still have to keep track and monitor how we are impacting the aquifers underground. So we want to avoid contaminating them, right? So if you do inject things underground, you want to monitor the quality. A lot of these water is also used for drinking and farming and for different communities. So as you can see, the subsurface space actually is pretty crowded if we wanted to use it for all these different purposes that are related to the energy. So I hope you enjoyed the video and learn a little bit about geoenergy or energy in the subsurface space. I hope I have convinced you that the subsurface space is actually very important for different applications related to the energy transition and addressing climate change. And I hope you enjoyed the video, and there are more interesting information in the Future Energy Systems Learning page. And have fun at the event.